When we picture a planet-ending threat from space, we naturally imagine something huge, a miles-wide rock casting a shadow over the continents. But out in the cosmos, size is actually the wrong thing to worry about. The true destructive power of an object comes down to how fast it's moving. To see how extreme velocity breaks the rules of our everyday reality, let's drop two completely harmless items down to Earth: a piece of raw steak and a tiny sewing needle. Tracing the path of these two objects toward the ground illustrates why velocity, not mass, is the primary variable for cosmic destruction. We'll start 400 kilometers up, aboard the International Space Station. If a spacewalking astronaut accidentally lets go of a ribeye, it starts moving incredibly fast. As it falls, the air in front of the meat can't get out of the way quickly enough. That air compresses and gets intensely hot. There's no time for medium rare, though. The searing heat burns the surface layer to a crisp, while the stratosphere keeps the center completely frozen. That assumes it falls straight down. In reality, an object dropped from the station is subject to orbital mechanics. The meat would likely slip into a free-fall loop around the planet. Roughly 90 minutes later, it could come flying right back toward the station at 28,000 kilometers per hour. At that velocity, a standard dinner side dish packs enough kinetic punch to tear through the hull and wipe out the entire crew. That's the damage from a relatively slow orbital drift. Let's push things to the absolute extreme and accelerate our sewing needle to 99.9% the speed of light. For context, the fastest human-made object ever built is the NASA Parker Solar Probe. It maxes out around 635,000 kilometers per hour. But at light speed, you'd be covering the entire distance to the moon in a mere 1.3 seconds. Getting a physical object to travel that fast runs into a massive physics roadblock, courtesy of Albert Einstein's theory of relativity. This chart shows exactly what happens to an object under acceleration. As its velocity creeps closer to the speed of light on the bottom axis, its mass effectively curves upward. To push a physical object to 100%, it would gain infinite mass. You would need an infinite amount of energy to keep it moving. That's a physical impossibility. But if an advanced civilization figured out a workaround to hit 99.9%, our impossibly small needle would arrive carrying the kinetic energy of a nuclear weapon. Let's direct that kinetic energy squarely at a densely populated target, New York's Central Park. The needle strikes with a blinding white flash, releasing an enormous heat wave that incinerates the immediate surrounding area. The ground impact triggers a massive 7.3 magnitude earthquake, toppling skyscrapers and rocking neighboring states. If we aim the needle at the middle of the ocean instead, that same million tons of TNT equivalent explodes underwater, displacing enough liquid to blast a plume 2 kilometers straight up into the air. You might expect a tidal wave to follow, but an explosion at a single point doesn't displace water over vast areas the way shifting tectonic plates do. The coastlines would be spared a tsunami. The absolute worst-case scenario happens if this tiny piece of metal lands exactly on the site of an active volcano. The immense impact force violently fractures the surrounding subterranean rock, instantly blowing the lid off the pent-up pressure below. This disruption triggers a super eruption, comparable to the ancient Toba event that nearly wiped out early humanity. The immediate blast is just the start. Volcanic ash injected into the upper atmosphere blocks the sun's rays for a decade or longer. Temperatures plummet, carbs die, and the ensuing collapse of the food chain ultimately drives most terrestrial life to extinction. By triggering a decade-long volcanic winter and the collapse of the global food chain, this single gram of metal causes an extinction event usually reserved for mountain-sized asteroids. Kinetic energy acts as an exponential multiplier, meaning that at relativistic speeds, even a sewing needle matches the destructive potential of the world's largest nuclear weapons. Einstein's speed limit restricts our ability to travel to the stars, but it also provides a critical structural safeguard for planetary life. If matter could freely accelerate to the speed of light, a single grain of stray cosmic dust could hit our atmosphere and shatter the Earth. While the physics of high-velocity impacts holds terrifying power, the unyielding math of the cosmic speed limit remains our invisible, unbreakable shield.